I've got this old Black & Decker cordless trimmer. You can see it's charging. It's been charging all night. So let's just try it here. You can see it's completely dead. Haven't used it for a while. It's probably the battery, but let's get it apart. It's got a bunch of T15 torque screws. Let's get them out. So there's the battery. It's lead acid, 3.3 amp hours, 12 volts. It's kind of a, looks like a uninterrupted power supply battery. Let's get it out here. Let's try it. Okay, so 0.85 volts. Again, that's been charging all night, so it's definitely shot. Let's just make sure the charger's okay. Yeah, so it's putting out almost 15 volts, so definitely the battery. I know I did replace this at least once. That was a few years ago. Don't remember exactly how long it's been. Of course, could just buy a new battery. But the performance of this thing is not the greatest. When you have a new battery, it runs for maybe 20 minutes. Then you have to charge it overnight. After a year or so, it goes down to maybe 10 minutes of runtime. And you still have to charge it overnight for every 10 minutes. So it'd be nice to have a little bit better performance. So I think I'm going to try to convert this to either nickel metal hydride or lithium. So let's just see what we can fit in here. Okay, so the old battery is 3.3 amp hours. I'd like to at least double that. So as far as choice of battery chemistry, I was first thinking of nickel metal hydride, maybe 10 nickel metal hydride C cells. That would give nominal 12 volts, peak of about 14 volts. But that's only 5 amp hours. And this thing draws probably about 10 amps, so that's a little bit low. So then I was thinking maybe nickel metal hydride D cells. You can get these at 10 amp hours. So that would be fine with a 10 amp load, but you can't quite fit 10 in here. You can fit 8 in easily, but no matter how you arrange them, you just can't fit 10. Also considered AA nickel metal hydride cells. I could actually fit 40 of these in the space. That again would give about 10 amp hours, but it's just a lot of soldering. Of course, there are some advantages to these nickel metal hydride cells. They're pretty much self-balancing, so you wouldn't need a battery manager. Probably would have to get a special charger. They do sell chargers for 10 nickel metal hydride cells in series. But again, that's just a lot of soldering and kind of messy. So I started thinking about using lithium cells, specifically lithium iron phosphate. And those have several advantages. Of course, the voltage is much higher, 3.2 volts instead of 1.2 volts per cell. So 4 of these in series are perfect for 12 volt equipment. Also, lithium iron phosphate cells, they can tolerate very high current draws, actually much higher than we need. They can also be charged at a higher current, so in theory, faster charging. So these specific cells are from K2 Energy. The form factor is 26650, in other words, 26 millimeters in diameter, 65 millimeters long, so they're just a tiny bit larger in diameter than a C cell, and about 50% longer. So as far as fitting these into the trimmer, I can fit 4 of these on this side quite nicely. It almost seems as if the trimmer was made for these cells. And then I'll put 4 more on the other side, so a total of 8. So we'll have 2 in parallel and 4 in series. And these are 3.8 amp hours per cell, so 7.6 amp hours total. That's about 2.5 times as much as we had with the lead acid. Of course, you have to be somewhat skeptical of these amp hour ratings, especially in this case, because this is 3.8 amp hours is quite a bit higher than most 26650 cells. Unfortunately, there's a guy on YouTube who actually tested these and found they were very consistent and spot on at 3.8 amp hours. So as far as cost, I got these from batteryhookup.com. They were a little over $2 a piece, although with shipping it's more like $3.50 a piece. So 8 of them going to be $28 worth of cells in the trimmer. So the main disadvantage of lithium cells is that they can be ruined by overcharging them or over discharging them even once. So really you should have a battery manager to control that. So found this little battery management system. It's specifically designed for 4 lithium iron phosphate cells in series, and it's sort of a plug and play thing. All you have to do is hook this up, and it will control the discharge, turn it off when the cells get too low. Also control the charging, turn off the charging if the charge starts to get too high. And the rating is up to 30 amps discharge. That's much more than we need. We probably only have about 10 amps discharge current. And we certainly won't be charging it at anywhere near 15 amps. So this has two thick connections here, and this controls the charging and discharging. And then we have this cable of much thinner wires, and this controls the balancing between the cells. So at least in principle, we can just install this, and it'll take care of the charging, control the discharging, as well as keep the cells in balance. So I'm just going to wire this up here. Okay, I've got 8 cells all wired up here, 2 in parallel and then 4 in series. And I've got the balancing connector to the BMS, also wired up to the cells. Of course, lots of videos on how to solder these cells. Apparently it's okay to solder them as long as you do it quickly and don't heat them up. And they tell you before connecting this to the BMS that you should check each adjacent connection to the cells just to make sure you have it wired correctly. So let's do that. So black is the negative here. So here's the first cell. 3.3, second cell. 3.3, third cell. And fourth cell. And then here's the whole string. 13.2 volts. Okay, so it seems to be wired okay. Now they tell you to check the BMS to see if it's working, and the way you do that, turn this to the continuity setting. And we're going to check the B minus in, and basically this is the B minus out. And without the cells plugged in, of course, this should be open circuit. Open circuit. And then plug it in, and with the cells in this state of charge, we should have continuity in both directions so that the cells can both charge and discharge. Try the other direction. Okay, so cells are working, the BMS is working, and then just have to wire up the power lines on the BMS. So one little detail, this actually has a little circuit board in here with a diode on that. And what that does is that the charging current goes through the diode, and then there's an LED on the charger side. And that's so that the battery can't power the charging light, and it only goes on when it's charging. But since the charge has to go through that diode, and that's only a 1 amp diode, we want to charge it at 3 amps. So I'm going to put in 5 amp Schottky diode, which will have less of a voltage drop and be able to handle that current. Okay, so we're all wired up, and I've just made one final addition, and that is a little dongle coming out of the side here that goes directly to the batteries so I can measure the charge. And just have to get this back together now. Okay, we're all back together. Let's just measure the voltage here. And we're at 13.16 volts. Just give it a try. Seems to be running anyway. So take it out and do some trimming. Okay, that's been trimming about 15 minutes now. Still running, but the power is starting to fade a little bit. Let's just see what the voltage is here. 12.85. So that's about 3.21 volts per cell. That's maybe, I think, 30% charge, 70% discharge. So what about a charger? Well, of course, we've got the old charger, and here it is. Kind of hard to read, but if you look right here, it says 260 milliamps, 13.5 volts. So this used to charge it overnight, but now that we've got 7.6 amp hours, this is going to take roughly maybe 30 hours to charge it, which is certainly less than ideal. And of course, I do have an extensive collection of chargers. So found this one. Not sure what this is from, but it's 15 volts, which would be okay. 850 milliamps. So that would charge it in maybe 8 or 9 hours. So let's plug it in here. Measure the voltage. $20 volts. So that might work, but it's really a little high. Well, I've got this one. I think this was from a Dell monitor. And it says 14 volts at 3 amps. So that voltage is perfect, and 3 amps would probably be okay for a charging rate. So let's just check this one. And it's putting out just about exactly 14 volts. Let's plug in the charger and see how it charges. This is this Dell 14 volt adapter again. And we'll put it through the ammeter here. Charging at about half an amp. Expected it to charge a little faster than that. Let's see what the voltage is. So voltage to charge of 1386. And the voltage at the batteries, 1314. So 0.7 volt drop between the charger and the batteries. Well, it is going through that diode as well as the BMS. So maybe that's to be expected. Well, let's try this other power supply. This is the one that said 15 volts, but it actually measured 20 volts. Supposedly 850 milliamps. So let's try that. Again, we'll use the ammeter here. So that's actually a little better. It's charging at 1 amp. Let's read the voltages. This is at the charger, 14.31. And at the batteries, 13.41. So about a 0.9 volt drop. Well, that's a little better, and we'll just watch it. Again, this was 20 volts with no load, but I don't think it will overcharge. The BMS is supposed to prevent that. So I'll just monitor it and make sure it doesn't overcharge. And maybe this will be a better choice. Okay, we're at 5 hours of charging. Battery voltage exactly 14 volts, so that's 3.5 volts per cell. I think we're finally getting close to a full charge here. And the current still almost 1 amp. So we put in about 5 amp hours. And I think they have to be pretty close to fully charged. I'd like to see if the BMS actually turns off, but I think at this point I'm going to just leave this and try trimming with it, see how long it lasts. Okay, we've been trimming about 20 minutes now, so the lead battery would have been completely depleted by that point, and we're still going. Let's just see what the voltage is. So 1333, 34, that's 3.335 per cell. So I think that's still at least about 50% charged. So definitely an improvement from before, and I'm going to go do some more trimming, see how long it lasts. Okay, I've been trimming continuously now for 1 hour, which is 3 times as long as it ever did with the lead acid batteries. But it does seem to be losing a little bit of power. So let's just see where we are here. 12.72. So that's 3.18 per cell. I think that's maybe like 75% discharged. Now I know we could recharge with the 15 volt charger, probably take 7 or 8 hours, but I did find yet another charger, and this is an old laptop charger, and it says 3.36 amps at 16 volts. So if this works, the advantage of this would be that it can't possibly overcharge the batteries. This one, open circuit, it reads 20 volts, so theoretically if the BMS failed, it could overcharge the cells. So I'm going to try this this adapter, see how that works as a charger. Let's just check the open circuit voltage here. Yeah, so 16.4, that's a lot closer to what we want. Okay, so we're charging, and I've got a clamp meter here to measure the current. Okay. Ah, this is charging at almost 4 amps. So that's actually a little bit above the rating of that AC adapter. And maybe a little bit higher than we want, really. So I've got a 0.12 ohm resistor. Let's see what happens if we put that in the circuit. So now we're getting 3.36 amps, which is just about the rated capacity of this adapter. And finally, let's measure the voltage drops on the diode and on the BMS. So the negative pole will give us the voltage drop on the BMS. So 0.6 of a volt. And if we measure from the positive side of the charger to the positive pole of the battery, that should give us the voltage across the diode. And that's just about 1 volt, which is a little high, but probably some of that is just in the wiring. So I'm just going to go ahead and let this charge and see how that goes. Okay, it's been charging 1 hour now. See what the current is. .97, so still almost 3 amps. Okay, we've been charging 1 hour and 45 minutes now. And let's just see what the voltage is as it's charging. This is the actual battery. 14.8. So that's 3.7. That's where you're supposed to stop charging these cells. So let's just measure the current quickly here. And just about exactly 2 amps. Let's turn this off. And if we calculate from the current, I think we put about 5 amp hours, maybe 5.1 or 5.2 into the battery. So you'd think they'd be pretty close to charged. So actually, as long as we're this close to a full charge, I thought I'd just let it keep going and see if we can get this BMS to turn off at full charge. So I've got voltmeter connected directly to the batteries and clamp meter on the charging line. And I'm just going to plug this in. So we're going at 14.3 volts, 2.25 amps, and by the time this gets up to 15, we should see it turn off. And there it goes, going down to just about 0. And of course, as soon as it does, the voltage starts settling down. And when it gets just about to 14, which is 3.5 volts per cell, then it turns back on. So presumably you could just leave this and to keep it fully charged, although probably better for the batteries to disconnect it once it hits a full charge. So I think we could have used any of these charges really. The Dell would have been a little bit slow at recharging it. Could have used the 15 volt charger, recharging it at 1 amp. That would have taken about 5 hours to recharge. And even though that power supply has a open circuit voltage of 20 volts, of course the BMS does seem to work and would shut it off before it overcharges. But I think this ThinkPad laptop supply, 16 volts, is really the optimum. And you can get these real cheap. This is like $10 on eBay. And this will charge it in about 2 hours, and then you get a runtime of 1 hour, which is a big improvement over the lead acid, which was 20 minutes of runtime and then an overnight recharge. Plus, I think these batteries will last quite a bit longer than a lead acid battery. Actually, probably the motor will wear out or something else will break before these batteries wear out. I kind of like this little BMS, although the lower cutoff voltage, 2.2 volts, seems a little low. I'd rather it were more like 2.7 or 2.5, which is what the battery manufacturer recommends. But I think you'd see a drastic loss in power way before it ever got that low, so it shouldn't be that much of a problem. But it's nice that it's all configured. All you have to do is wire it up, and it should work with any piece of 12-volt equipment as long as you can find batteries that fit. Thanks for watching.